we started PMIs, right? Proof by mathematical induction, right? And we did the one to divisibility only, right? Remember the main steps? We had to show it holds for n equal to 1. And then we had to assume right? Assume it holds for n equal to k. And then we had the main step, right? Show it holds for n equal to k plus 1, right? Let's see if we can try a few now. So today now, I'm going to just give you one hard one with the divisibility, and then we go into this summation type, right? So I want you to prove by mathematical induction, right, that 3 to the 4n minus 1 is divisible by 16 for all values of n more than or equal to 1. Right? Do the usual steps, right? That's 80, right? Which is 16 by how much? 5. Right? Therefore, divisible by 16. I will make 3 to the 4k the subject of the formula, right? And now, I have to show it holds for n equal to k plus 1. Okay? So all I'm going to do is I'm going to write 3 to the 4. This is important. You put open brackets, k plus 1 minus 1 is equal to 16. You can change the letter to b. Right? So we're focusing on the left-hand side. So the left-hand side is 3 to the 4 by k plus 1 minus 1. Then multiply it out. You'll get 3 to the 4k plus 4. Right? Most people who get this wrong, they wrote 4k plus 1 instead of multiplying out the brackets properly. So this will be 3 to the 4. Right? And let's finish it up. 3 to the 4 is 81. Right? By, so I'm going to put that part in here. So that'll be 16a plus 1 minus 1. So that will be 81 by 16a. I don't have a calculator, right? Plus 81 minus 1. So that's 81 by 16a plus 80. Now I can factor out 16 and I will get 81a plus 5. Right? It don't really matter what the value is once you can do this. And you can say is of the form 16b. So you're good to go. Therefore, by proof by mathematical induction, and you write out the step I gave it. It holds for n equal to 1, n equal to k, n equal to k plus 1. Therefore, it holds for all n more than or equal to 1. All right. So we're going to apply this now to questions that instead of having divisibility, they have summation. Right. So before I study PMI, I just want to explain summation. Right. Head up summation. So if I told you the summation of R going from 1 to n of, let's just say R, right? All that means is that we summon all the terms of R. We summon all the terms of R until we reach n. So we summon 1, that's the first term for R, then 2, then 3, then 4, all the way until we reach n. So a small example. If I told you the summation of R going from 1 to 5 of 2 to the power of R, right? So you just summon all the terms until you reach R is 5. So the first term, R is 1, You add in that to second term, R is 2, third term, R is 3, R is 4, R is 5, right? That's basically the principle behind this summation, right? What you're going to need now is you are going to need to understand a few little things when you're doing the PMIs, right? One of them is this. If I were to add this, right? If I want to write that, that's the summation of R going from 1 to 4 of 2 to the power of R. And if I add that to 2 to the power of 5, then this statement here, this whole statement here, right, is the same as the summation of R going from 1 to 5 of 2 to the R. So what you're going to see in PMIs is you are going to see the summation of this plus this term is called the K plus 1 term. That's the term right after this, right? That's the K plus 1 term, and this here is the summation of R going from 1 to K of whatever the function is. Let's call the function AR. So what you're going to learn in PMIs is that whenever you add the summation of R going from 1 to K to the K plus 1 term, what you're going to get is the summation of R going from 1 to K plus 1 of e to the R. So the main thing I want you to gather from this is that whenever you summon R going from 1 to K plus 1 of any function, let's call the function e to the R, right? Any function you want, right? Is the same as the summation of R going from 1 to K plus the K plus 1 term. The K plus 1 term is simply the last term, right? It's just simply the last term. So for example, if I wanted you to work to write this to me, let's say it's 2R plus 1. Let's say that's the function. How am I going to write that? Well, you're going to write it like this. The summation of R going from 1 to K, right, to K of 2R plus 1 plus the K plus 1 term, right? Because that's the rule that we're using, right? If we sum all the terms plus the K plus 1 term plus the last term, we'll get a total summation, right? So what is the K plus 1 term? The K plus 1 term, this is the last term, right? How do I get the last term? Real simple. Just take K plus 1 and put it in there. Just like how you put R as 1 and R as 2 and R as 3 and so on, all you're going to do is put K plus 1 in that formula, right? Wherever you have R. So it will be 2 by K plus 1 plus 1. Then you simplify that out. This is what you're going to need in PMIs. Okay? So whenever you sum those two, you get the sum of the K plus 1 term. Right? There are some other rules that we need to learn, right? But you will honestly, you won't use them right now, but you need to know the rules. If you were to sum R going from 1 to N of A to the R plus the summation of R going from 1 to N of B to the R is the same as you summon R going from 1 to N of A to the R plus B to the R. Same thing with minus, right? And next thing you could do is if you have the summation of constant, the summation of constant is simply the constant multiplied by the total number of terms. Right? This is the most important rule here. That's the one that we're going to use more of now, right? So this is the most important slide. For those who screenshot this one here. Right? So this a little bit longer. The hard step is being able to factorize properly. So let us prove by mathematical induction that the summation of R squared, R going from 1 to N, we have to prove that is equal to 1/6 by n plus 1 by 2n plus 1. So same 3 steps. We're going to prove it holds for n equal to 1. We're going to make the assumption, then we're going to prove n equal to k plus 1, right? So let's start. So when n is equal to 1, we start with the left-hand side. The left-hand side is basically just one term, so that's 1 squared, which is 1. Then we go with the right-hand side. The right-hand side, we just plug in 1, right, into the formula. So that's 1/6 by 1 plus 1 by 2 by 1 plus 1. 3 by 2, that's 6 by 1/6, that's also 1. So therefore, it holds for n equal to 1. Next step, we're going to assume it holds for n equal to k. So this is the assumption step. So all we're going to do is just wherever we have n, take off n and put k. So we'll be going to get the summation of r going from 1 to k, because I'm taking off the n, right? Of r squared is equal to 1/6 k by k plus 1 by 2k plus 1. Okay? And we're going to use this, right? We're going to use this later on. So I'm going to put a little star here, right? Because I'm going to use that in the proof in a little while, right? So assume it holds for n equal to k. Now, here's the tricky part. So we have to show it holds for n equal to k plus 1. I'm going to go it over, right? Everything here, you're just going to, when I change the question, all you're going to do is just change the numbers. Okay? So show it holds for n equal to k plus 1. All I'm going to do, I'll take up n in the beginning and put k plus 1. So the summation of r going from 1 to k plus 1 of r squared is equal to 1/6. Instead of writing k, I'm going to put k plus 1. Instead of writing k plus 1, I'm going to write k plus 1 plus 1. And here I'm going to write 2. Notice I'm going to put my brackets because I don't want to make a mistake and simplify it wrong. So I'm ending up with 1/6 k plus 1, k plus 2, 2k plus 3. Right? The objective of the whole proof now is to be able to prove this part here. Okay? So I'll just put in a little statement here. We're trying to prove, right? So I'm trying to prove that this left-hand side here is equal to this right-hand side here. Right? That's the objective of everything now. So I'm going to write left-hand side, right? Summation of r going from 1 to k plus 1 of r squared. So I want to prove that. Now we go back to what we did a little while ago, where we said that the summation of r going from 1 to k plus 1 is the same as the summation of r going from 1 to k of r squared plus k plus 1 2. Okay, so what do I do now? Now I am going to, let me write one more step before I make substitutions, right? I already know what the summation of r going from 1 to k is. See this here? That's the star. That's this star right here. So I'm going to write back that statement. I know what this is. That is equal to this. Okay? So I'm going to write that. I'm going to write 1/6 k plus 1, 2k plus 1. What is the k plus 1 term? The k plus 1 term is always going to be substituting k plus 1 for r in here. Whatever they give you there, just substitute k plus 1. And I'll get k plus 1 squared. Once you understand the principles of PMI, up until here is the easy part. After this is the hard part. We need to figure out how to make this fella here look like this fella here. We're trying to prove that. Okay, so let's see if we could do it, right? So the first thing I'm going to do, I'm going to just factorize, right? Because everything there is a whole set of products in the proof. So I'm going to factor out 1/6, and I'm going to factor out k plus 1. What would I be left with? I'll be left with k here and 2k plus 1, right? If I factor out 1/6 from 1, because remember, this is 1 by k plus 1 squared, right? Here what will happen? Instead of writing 1, I'm going to write 6 on 6. So if I factor out 1/6 from 6 on 6, I'll get 6. And if I factor k plus 1 from k plus 1 squared, I'll get k plus 1. Right? And that's the bracket part. Right? You see that fraction part that people make a lot of mistakes, right? If you factor out 1/6 from 1, you will get 6. Because 6 by 1/6 gives you back 1, right? And you'll be left with 6k plus 1. Multiply out inside here, you'll get 2k squared plus k plus 6k plus 6. You'll get 1/6k plus 1. You'll get a nice quadratic in here. 2k squared plus 7k plus 6. Right? We'll have to factorize that quadratic. And if you know you can't if you struggle with factorization a little bit, then multiply this out and you'll get this. Okay? That's the next option if you want. Right? If I factor out that, I'll get 2k and I will get I want to get 7, right? So I'm putting the 2 here and the 3 here. Plus. And that's it. That's identical to what I have. So I could do my little box here. And then I could see, since it holds for n equal to 1, n equal to k, n equal to k plus 1, then by proof by mathematical induction, right? It holds for all n. I think this was more than 1, right? I didn't write it on top. More than or equal to 1. And that's it. It's not a difficult thing, but where it becomes challenging is right here. See that factorization to work out that? That's where the challenging part comes in. Some easier, some more challenging to factorize, right? Copy it down. I'll give you one easy one and then a few hard ones, right? Prove by mathematical induction that the summation of r going from 1 to n of r is a half n by n plus 1, right? For all, I think it's natural numbers or something. Go ahead, do your thing. When n is 1, left-hand side is 1 basically. Right-hand side is a half of 1 by 1 plus 1. Half of 2, which is 1. Right? N equal to k. You're going to write the summation of r going from 1 to k of r is equal to half k by k plus 1. And then k plus 1 is where we're trying to prove this, right? So that'll be the summation of r going from 1 to k plus 1 of r is equal to 1/2 of k plus 1, and then take up n and you'll get k plus 1 plus 1, which is k plus 2. So usual thing, we're trying to prove this, and we are going to use this in our expansion, right? So you start with the left-hand side here. You have the summation of r going from 1 to k plus 1, right? That's the summation of r going from 1 to k plus the k plus 1, 2. Okay, r going from 1 to k, and then you add the k plus 1 term, So remember, you could take off this and write this. So that'll be 1/2 k, k plus 1. And then you add it to the k plus 1 term, k plus 1 term, just put k plus 1 wherever you have r in there. And you'll get k plus 1. If you factor out 1/2 k plus 1, you'll be left with k here. And if you factor out 1/2 k plus 1, you'll be left with 2. And if you look at it, this is what you're trying to prove. So you have it. Write the line, right? Since it holds for n equal to 1 and so on, right? Prove by mathematical induction that the summation of r going from 1 to n for r minus 3 is equal to n by 2n minus 1. So let's go with n is 1, left-hand side. Right, that'll be 4 by 1 minus 3. That giving you 1 again. Right-hand side, 1 by 1 minus 1. So that's what? 2 minus 1 is 1 by 1 is 1. Right? N equal to k, summation of r going from 1 to k, 4r minus 3. Remember, you only replace n with k and not r. So you'll get k by 2k minus 1, right? And then n equal to k plus 1. That'll be the summation of r going from 1 to k plus 1 of 4r minus 3 is equal to k plus 1 by 2 by k plus 1 minus 1. Notice I have my brackets there. So I'll get 2k plus 2 minus 1. That'll be 2k plus 1. Right? It's important to multiply that out properly. So this is what I'm trying to get. So I'm starting with the left-hand side. Right? That's the summation of r going from 1 to k plus 1. Right? We know what this left-hand side is. Summation of r going from 1 to k of 4r minus 3 plus the k plus 1 term. Right? That's the same all the time. When I make my little substitution, right, I'm going to replace this with this, and I will get k by 2k minus 1. How do I get the k plus 1 term? How do I get the k plus 1 term? Right, to get the k plus 1 term, just take off r in here, right? So that'll be 4 by k plus 1 minus 3. So that'll be 2k squared minus k plus 4k plus 4 minus 3. So I just kind of multiply it out, right? So I'll get 2k squared minus k plus 4k is plus 3k plus 1. Right? When I reach here now, I will obviously, because of what I'm trying to prove here, I remember I'm trying to prove that there, right? I'll have some factorization to do. Again, if you can't factorize, expand this out and you will get that same thing there, right? So factorize it there, and what we'll get? 2k, k, 1, 1, and addition sign. And that's it, QED. And of course, write the last line since it holds for. All right, try this last one. 1 over r by r plus 1 is equal to n over n plus 1. N is 1, left-hand side, 1 over 1 by 2 is equal to 1 over 2, right? Right-hand side, it'll be 1 over 2. So they're equal, right? Therefore, it holds. N equal to k. Summation of r going from n, sorry, k, there's a k on top there, right? R by r plus 1 is equal to k over k plus 1. Now for n equal to k plus 1, that'll be the summation of r going from 1 to k plus 1 1 over r by r plus 1. This will be now k plus 1 over k plus 2. Right? Again, I'll go with the left-hand side. Summation of r going from k plus 1, 1 over r by r plus 1. Right? Main thing here is that you get in you make the right substitutions. So you're going to substitute for this. And then the k plus 1 term. Right, so the summation here, that will be k over k plus 1. The k plus 1 term is putting k plus 1 in that fraction. So that will be k plus 1 by k plus 2. Right, so your denominators will look like that. K plus 1, k plus 2. Right, remember substituting here. I substitute for r here and r here. Now for the hard part. The hard part is to make it look like this. Okay? How do I make it look like that? Well, I have two fractions. Here I have one fraction. So obviously, I'll have to find a way to find the LCM. So the LCM is k plus 1 by k plus 2. How do I simplify that now? How do I expand that out? Well, you have a few options, right? So when you multiply k plus 1, when you multiply by this, k plus 1 will cancel here, and you'll be left with k by k plus 2. In next side, k plus 1 by k plus 2 will cancel, and you'll get a 1. So you have to finish it, factorize the top. K squared plus 2k plus 1 all over k plus 1, k plus 2. That is not it as yet. You still have more things to do. You have to factorize the numerator. K plus 1, k plus 1 all over k plus 1, k plus 2. This will cancel, and you'll get it. Okay? And again, what it boils down to, right? Being able to simplify this. Okay, if somebody tried to factor out 1 on k plus 1, then you would have gotten k plus 1 on k plus 2. And then you have to find the LCM in here. And you'll end up with the same thing.